Hi everybody, welcome back. Now that in the last video we saw what a limit is, and we looked at kind of one way to find a limit, which is to plug in values that get really close to a value of a. And we got to remember to plug in values on the left side and on the right side because the left and right hand limits might not be equal. We have a way to be able to find limits now. The problem with that is it's a pretty tedious way to find limits. I don't know about you, but in any problem where we're given something that says find a limit, I don't necessarily want to have to calculate, 10 different things, 5 on one side, 5 on the other. That just seems a little bit tedious. In this section, we are going to be talking about some properties of limits, or you might call these things limit laws. And we're going to see kind of what are some of the ways that limits behave, what are some things you can do with limits, but then really what we're going to kind of, how we're going to kind of culminate this section is by looking at 3 different things that you can do to deal with limits. So first of all, let's jump into some laws or some rules about how limits behave. Okay, some of these may seem pretty intuitive and pretty straightforward, but we still need to kind of clarify and make sure that we know that these that you're allowed to do certain things when we have limits. For many of you, limits might be a completely new topic, and so you say, well, what am I allowed to do with limits? How do these things behave? What's allowed, what's not? That's a really good question to ask in math, and so that's kind of what we're going to look at first here is what are we allowed to do and what aren't we? Okay, so let's suppose, for example, we're talking about 2 different functions. Let's say we're talking about a function f of x and a function g of x, and we're going to look at the limit as x goes to a of f of x and the limit as x goes to a of g of x. And we're going to suppose that this a and this a are the same, so they're the same value. Okay. Some of these things are going to be pretty intuitive, the way that you would think that they happen. I'm going to label them kind of 1, 2, 3, 4 here, but this is going to be pretty straightforward, and we'll see a couple of examples of how these get applied as well. But let's say you're looking at the limit as x goes to a of something like take f of x, the function, and add it with the function g of x. Okay, I don't know if you have an intuitive idea of what you should be able to do here, but one thing that you can do with limits is basically you can take the limit of a sum of different terms, and the way you do that is you just take the limit of the first term and then the limit of the second term and kind of deal with them separately. So it is perfectly fine for you to say the limit as x goes to a of f of x, add the limit as x goes to a of g of x. Now be careful not to use the word distribute here, okay? You are not distributing a limit. That is not the correct terminology, but the idea still holds. It kind of says you can take the limit of both of the pieces, both of the terms there separately, okay? But the same thing is true whenever we're dealing with a lot of different kinds of operations. And so not just when you have addition in the middle here, but the same thing actually holds when you have subtraction. And so not just when you have addition of f plus g, but when you have f minus g, then over here on the right side, you can do the limit of f of x minus the limit of g of x. And so basically, when you have multiple terms in your, whatever your function is that you're starting with, you can kind of split up and deal with those terms separately. That's all that says. Okay, and actually, if this actually works for addition and subtraction, it also actually works for multiplication and division. Now I want to make a really important distinction here. So here's what that looks like. The limit as x goes to a of f of x times g of x. If you have 2 functions that are multiplied together, you can still do the same thing. You can still say, hey, let me handle the limit of each of those things separately, and take the limit of the first one, take the limit of the second one, and multiply the results together. Okay, so that's perfectly fine with multiplication there as well. In fact, it's actually true with limits with division. So this is horrible notation, I hope, but I think if I put this, you'll know what I mean. Like this works not just for addition and subtraction, plus or minus, but it also works when we're multiplying or when you're dividing 2 functions as well. I want to make a really important distinction though. Okay, later on here in chapter 2, we are going to deal with something that is the basis of all of calculus. It is something called the derivative. Okay, we'll see that in a few sections. We want to be really careful here because limits and derivatives do not always behave in the same way. This is a little foreshadowing of what we're going to see in a few sections. With derivatives, when we get there, the same thing is going to be true for the first one, okay, where when you add together or subtract two functions, you can take the derivative of the two functions separately and add or subtract their results over here on the right side. That is going to be true with derivatives later on. But the second one is going to not be true for derivatives. Now, you don't know what I'm talking about yet for derivatives, unless you've taken a calculus course before, but just kind of consider this some foreshadowing right now, is that when we get to derivatives, this second rule of being able to talk about multiplication and division, things do not work that same way when we're talking about derivatives in the future. You can use rule number 1 with addition and subtraction, but for now we're just talking about limits. So for now, just keep in mind that when we're talking about limits, you can have addition and subtraction of functions or multiplication and division of functions, and you can take the limit of each of those separately, individually, and then use that operation in the middle to combine them back together. Too surprised to hear about these other ones, which is that when you have a limit as x goes to a of, I don't call it like this, how about x to the n power, where n is some constant. You can also do this where you'd have something like the limit as x goes to a of x, and then raise your result to that constant n. Basically just kind of says you can move the limit inside and only worry about the part that has an x in it. Since n is a constant, it doesn't have an x in it. It's kind of like having a constant out in front. It doesn't have an x in it anyways. The limit as x is kind of changing or moving doesn't affect that exponent in any way. So just go ahead and plug in the value of a there if you can for x, and then whatever your result is, raise it to the n power. This actually works with roots as well. That means that the limit as x goes to a of any root, I'll call it the nth root of x, or I tell you what, how about even not just an x inside, but an f of x inside, means you can also kind of move the limit inside of the root. Again, the nth root there doesn't have anything to do with an x, so you can just move that inside and say, well, this is the limit as x goes to a of f of x, and now your limit is on the inside. But again, that's only because the nth root that you have there doesn't have anything to do with an x, just like how the exponent didn't have anything to do with an x as well. Okay, and then the last one that I would call, I guess, a rule or a law is kind of one that we already saw as well. Again, a lot of these are intuitive, and it's what happens if you have the limit as x goes to a of just a constant. But the idea was that it's just that number. So if you have the limit as x goes to a of c, and by the way, oh yeah, c doesn't have, there's no x in it, so there's not an x in the part that just has a c. You actually just get c. Now, I think this one might be worth looking at a graph for. Let's say c is up here, and you have just a horizontal line. And wherever a is, okay, it could be over on the right and be positive, a could be over on the left and be negative, doesn't really matter. But if c is just some constant over here, then kind of think about y equals c as an equation would just be a horizontal line. As x goes to a from the left, or as x goes to a from the right, you're getting points on your line that are getting closer and closer and closer to this point right here in the middle. And what is the height of that point? Well, it's the same as the height of every other point. The height is c there, so you just get c as your output, saying that as x is getting close to a from the left or from the right, your output is approaching that point right there, which is at the same height of all of them. So again, not really, shouldn't feel like rocket science at this point, but it is just good to think about, hey, what happens if I have a constant in there? Okay, so a lot of these are some different rules, and we're going to look at maybe a couple. So these ones are more intuitive. They're I don't think there should be a ton of issue here. Basically, it's just you can move limits into stuff or move them around stuff that doesn't have an x in it, constants in certain places. So I tell you what, instead of trying to give you 15 different rules and say you need to know exactly what rule to use when and all this kind of stuff, I want to help you out. I want to kind of break this down into 3 ways to deal with limits. Now, these are in order. you should use method number 1 first. And if that doesn't work, then you should move down to method number 2. If that doesn't work, you should move down to method number 3. There will be a 4th method later on in chapter 4 when we deal with something called L'Hopital's rule. But for now, this is going to be able to get us to deal with kind of more common functions that we know, as well as some weirder, more obscure functions. And we can be able to handle a lot of different kinds of limits. So the first one, based on what we've done so far, I think the first method or the first way to deal with limits I hope should feel fairly intuitive now after all of the different times that we've kind of applied this without really talking about it, which is this. I'm just going to say for the limit as x goes to a of f of x, plug in a for x. Or another way to say that is find f of a. Okay, now we got to be careful with this because what we saw in a previous example is that you can't always do this. Okay, you might remember from the last video we had an x minus 1 squared on the bottom of a fraction and we were trying to plug in x equals 1. We weren't allowed to do that because that wasn't in the domain. So I'm going to say plug in a for x if possible. Okay, if possible, in other words, meaning if a is in the domain. And we'll see examples of all of these, but that's a good place to start. Sometimes you can do that and you're already done at that point once you plug in. Sometimes you can't. Okay, so what do you do if you can't just plug in a value? Well, here's my suggestion, is simplify the function if you can. Okay, now simplify could mean a lot of different things. We'll take a look at a couple of different examples of what it means to simplify. One example that you should already be really familiar with is dealing with rational functions from your past, and simplifying would mean factoring on the top and on the bottom of a fraction and trying to cancel anything that shows up on top and on bottom. In other words, you're trying to get rid of wholes. Okay, so simplifying, that's one way you can simplify. We'll talk about how to simplify a function that might have square roots in it. So there's not always a one-size-fits-all answer for how do you simplify. There might be a few different things you could try depending on what type of problem you have, but look for ways to be able to simplify the function if you can. After you can simplify the function, then plug in a. Okay, so in other words, if you simplify and you've kind of removed a problem area or you've probably removed a hole is what you've done, then you're kind of going back up to method number 1 and saying, okay, can I plug in a for x? Okay, if I'm allowed to do that, go ahead and do that. Okay, these two methods are definitely number 1 and number 2. You should try these first. Okay, you should not run down here to method number 3. I'm going to call method number 3 a last resort. I'm going to say, look, if you can't plug in a value, if you can't simplify, if you can't do anything else algebraic, then it kind of goes back to what we talked about in the last video, in the last section, which is estimate. Okay, anytime you hear the word estimate, you should think, oh, that's probably shouldn't be my first thought or my first thing I want to try, because it's kind of like a last resort. Like all else fails, try to get as close as you can. So estimate the limit by plugging in values really close to a. Now, this is what we did in the last video, but remember what we said in the last video, and be careful about this. You need to make sure that you're plugging in values close to a from both sides, okay, not just from one side, because remember, if you only plug in values from one side, then all you're finding is either the left-hand limit or the right-hand limit. You need to plug in values in from both sides so that you're seeing, does the left-hand limit equal the right-hand limit? Because remember, if the left-hand limit and the right-hand limit aren't equal, then this limit doesn't exist in the first place. And by the way, it is always possible when you're talking about a limit for the answer to a limit problem like this to be does not exist. That could be a possible option with all of these. You got to be careful. Do you get the same thing when you look at a left-hand limit versus a right-hand limit?